In this section 3.6.2, we are going to study what is a homogeneous catalyst and why is it able to act as one. So you learned in the previous videos that homo means same. It means that the catalyst is in the same phase as the reactants. Why are certain transition elements and compounds able to function as homogeneous catalysts? The real reason is this. Please put an asterisk here. It's due to their ability to exhibit variable oxidation states. For example, I'm going to give you an example. Fe2 plus and Fe3 plus is our classic example. And not just the ability to exhibit variable oxidation state, what is equally important is that it is easy to interconvert between different oxidation states of the transition metal ions. It's not difficult. It requires very little energy. It's very easy. Okay, therefore, it's possible to provide an alternative pathway of lower activation energy and therefore to increase the speed of the reaction or the rate of the reaction. So let's take a look at a concrete example, the oxidation of iodide ions by peroxyl disulfate, S2O8 2-. This reaction is extremely slow without the presence of a catalyst. Are you able to think of the reason? The reason is quite simple. If you look at both the reactants, they are both negatively charged. And since they are negative charged, they will repel each other, correct? And therefore, they will not want to react together. You need to supply a lot of energy to force them to react. So the activation energy is super high for this reaction between two ions that have the same charge. So what are you going to do to increase the rate of reaction? Okay, before we go on, okay, I just want to do some simple calculations of E0 cell to prove to you that yes, it is positive. However, we know that although the E0 cell is positive, the reaction is expected to occur radially between I- and S2O8 2-, but the activation energy is simply too high because you have two same charge ions, two negative charge ions. There will be repulsion. That's why I want to stress over here that E0 positive, a positive E0 cell value tells us that it is energetically feasible. Can you please take note? E0 cell positive means that the reaction is energetically feasible, but it tells you nothing about the rate of reaction. So kinetics and energetics are two different branches. So if E0 cell is positive, it automatically means that it's energetically feasible, but the kinetics may not be so. Okay, and in fact, the activation energy is very high, and therefore it is very slow. Okay, and the activation energy is high due to the repulsion between light charge ions. Okay, so I believe that at this stage you already know how to calculate the E0 cell, so I'm not going to go through this part in detail. Okay, let's move on. So what are you going to do to increase the rate of reaction? Okay, you need to throw in a catalyst, of course, because the reaction is very slow due to the repulsion faced by the two negative charge ions. So who can act as a catalyst? Just now we mentioned that the transition elements that are able to act as homogeneous catalysts is due to the ability to exhibit variable oxidation state and interconvert between them. So Fe2 plus could be a possible catalyst. So let's take a look at the mechanism for the catalysis with Fe2 plus as a catalyst. There will be two steps. The first step, okay, Fe2 plus will react with one of the reactants. How do you decide who Fe2 plus will react with? Okay, you think about it. Why in the first place Fe2 plus can catalyze the reaction? Firstly, you notice that the charge of iron 2 plus is positive. So if it's positive, it can attract the negative anions, the reactants. So Fe2 plus will then be able to react with one of them, either the negative I minus or the negative charge S2O82 minus. But which one is it? If you study carefully, I minus in this reaction is becoming oxidized to iodine. S2O82 minus is being reduced. Study the oxidation state. You will find that I minus, the oxidation state of I, the iodine, is increasing from -1 to 0. So an increase in oxidation state shows that iodide is oxidized. Whereas for S2O82 minus, peroxide disulfate, the oxidation state drops from +7 to +6 in sulfate. So a reduction in oxidation state means that it's being reduced. Peroxide disulfate is reduced to sulfate. So let's take a look. Since we say that we want Fe2 plus to catalyze the reaction, and we can prove this using E0. Okay, so bear this in mind first. So if we were to use Fe2 plus as the catalyst, I'm going to use yellow color. This Fe2 plus is the catalyst. What can happen to Fe2 plus? Possibly, it can be oxidized to Fe3 plus. And if Fe2 plus must be oxidized to Fe3 plus, then Fe2 plus must react with something that can be reduced. Do you agree? That will be peroxide disulfate. Why is that so? Because in a redox reaction, there must be one species reduced and one species oxidized. If you were to use Fe2 plus as a catalyst, and since Fe2 plus can only be oxidized to Fe3 plus, then your peroxide disulfate must be the one reacting with Fe2 plus to be reduced to sulfate. So one species is oxidized, Fe2 plus, one species, peroxide disulfate, is reduced. And you compute the E0 cell, and you find that it is positive. E0 cell is E0 reduction plus E0 oxidation. I'm sure you are very familiar with this by now. So E0 reduction is positive 2.01. E0 oxidation, please flip the sign, it is negative 0.77. And the E0 cell is positive. And you know that a positive E0 cell tells us that it is energetically feasible. This first step that we propose is feasible. What is Fe3 plus? What do you call this? Do you remember? In kinetics last year? Fe3 plus is what we call the intermediate. An intermediate is not a reactant. That means at the start, it was not there. But an intermediate is formed in one step of a reaction in the mechanism and consumed or used up in the next step. So let's take a look at what happens in the second step. Because no doubt, I have formed this product already, sulfate. I have already formed one of the product, sulfate. But I have not formed iodine yet. So my iodide must become iodine as well. So now this intermediate, Fe3 plus, is going to allow us to do that. Why? Because Fe3 plus will now become reduced back to Fe2 plus. Why? Because we need to regenerate back the catalyst. Fe2 plus was the catalyst, right? And now you need to regenerate back the catalyst, Fe2 plus. So the intermediate Fe3 plus must be reduced to the catalyst Fe2 plus. And the other species must be oxidized, because you know that in the redox reaction, one species is reduced, the other species is oxidized. So if Fe3 plus intermediate is being reduced, then it must react with a species that is oxidized, which is just I minus. Just nice. I minus is oxidized to iodine. Compute the E0 cell, and you will find that it is positive again, and the reaction is energetically feasible. Okay, so E0 cell is E0 reduction plus E0 oxidation, and E0 reduction is this value, positive 0.77. E0 oxidation is negative 0.54. And please do not forget to put the positive sign for E0 cell. BOD was given in some of the previous assignments, but please take notes that for the A-levels and your prelim or whatsoever subsequent test and assignment, we are not going to give you BOD. If it is a positive E0 cell, please indicate the plus sign. And it's a good practice to write that E0 cell is more than 0 and therefore conclude is energetically feasible. So what you have done over here is you have just proven that Fe2 plus can act as a homogeneous catalyst to catalyze the reaction between iodide I- and peroxide disulfate S2O82- successfully. And you'll notice that the mechanism of this catalyzed pathway, it occurs in 2 steps, and each step must be proven to be E0 cell positive. Okay? And the overall equation can be obtained by just adding up equation in the step 1 and equation in step 2. I want to point out there's a typo here you saw in red, 2. This is 2-sulfate. Okay, so take note of this. So if I were to combine the equation in first step and second step, that's how I get the overall equation here. So what I mean is, step 1, this particular equation, please add it up with this one. But you will realize one thing, the intermediate will cancel out. Do you notice that? Because the intermediate is formed in one step and used up in the next step. And the catalyst will also sort of cancel out because it's reformed at the end of the reaction. So you are left with 2I- plus this to give us sulfate and iodine. Normally, we will write the Fe2 plus on top of the arrow here to show that it's a catalyst. It's a homogeneous catalyst because Fe2 plus aqueous is in the same aqueous phase as your reactants, or aqueous. This alternate 2-step route offers a lower EA, a pathway with a lower, a pathway, an alternative pathway, can you change this part? An alternative pathway of lower EA. Because you notice that each step occurs between opposite charge ions. Do you notice? So you can think of Fe2 plus as the middleman. It's positive charge, right? So it can react with the one of the reactants, in this case peroxide disulfate. Positive, negative, attract. So the EA is lower. And this one also, I- is negative, Fe3 plus is positive, opposite charges attract. Lower the E. That provides a alternative pathway of lower EA. So if Fe2 plus can act as a catalyst, the reason is simply because it is able to exhibit variable oxidation state and interchange between these variable oxidation states with great ease. So from +3 become +2 easily. If Fe3 plus is used, it's fine. It can also work, but the 2 steps will occur in the reverse order. You go and work out yourself. The overall equation is still the same. And what other transition elements and their ions can be used? We can also choose to use cobalt 3 plus / cobalt 2 plus and manganese 3 plus and 2 plus. Okay, as long as it's flanked between the iodide E0 positive 0.54 and the peroxide disulfate and sulfate E0 positive 2.01. Okay, as long as the E0 value is in between these two, they can work, and you can prove it yourself. Okay, as a take-home exercise, go ahead and do it yourself to calculate the E0 cell for cobalt 3 plus, cobalt 2 plus, and prove that the E0 cell for both steps is still positive and therefore energetically feasible.